In this lecture, we will study the linearized subsonic and the supersonic flow. So this is a very first mini lecture. It's about the subsonic flow, and later on we will study what happens in a supersonic flow. Okay, and so earlier we know the 2D linearized perturbation velocity potential equation. So it's written here. And there's a short question for you. Do you still remember how this equation was derived? And basically, it's from the full velocity potential equation, and then we do the linearization. And here is a question. So we try to explain the subsonic and supersonic flows through this example. And apparently, we can see a VV wall structure as a flow So consider subsonic flow with an upstream Mach number of m infinity. This flow moves over a VV wall with a contour given by yw, which is a wall profile, and h times cosine 2 pi x divided by L, where yw is the coordinate of the wall, h is the amplitude of the wavelength, and L is the wavelength of the wavelength. Assume that h is small. Using the small perturbation theory of this chapter, derive an equation for the velocity potential and the surface pressure coefficient. So this is a task. We will derive an equation for the velocity potential and the surface pressure coefficient. So we will use this opportunity. Which opportunity? The opportunity to solve this problem, to review how to solve the subsonic flow problem. And the aim is to review the velocity potential and the surface pressure coefficient. Okay, so we have the linearized velocity potential equation. So we can assume phi xy, so which is perturbation velocity potential, is a multiplication of x and gy. Okay, by combining these two, we can rewrite the equation, the governing equation, in this way. And we can walk further by reorganizing the two terms in the equation. Okay, so we can separate the governing equation into two parts, one including the g, the other part including the f. So we will work on these two equations separately. And for the g equation, we can rewrite again. And so based on the theory of partial differential equations, we can have the theoretical solution of gy expressed this way. And similarly, we have the equation for f, PDE for f. And again, we have the theoretical equation for fx. So it's b1 times sine kx plus b2 times cosine kx. And the parameters of a1, a2, b1, b2, and k are to be determined by applying the boundary conditions. So now the task is to define a1, a2, b1, b2, and k. Okay, so let's list the boundary conditions. So boundary condition 1, when the flow goes to infinity in height, the velocity and also the gradient of perturbation velocity potential must be finite. So they cannot increase to an infinite value. This is the first boundary condition. And we have the second boundary condition, which is about the wall. So the flow at the wall must be tangent to the wall. Okay, so in this case, we have this is flow deflection angle at the wall. And so VW prime divided by V infinity plus UW prime, that's a velocity triangle. Okay, because we are assuming small disturbance or small perturbation, UW prime is far smaller than V infinity. In this case, we can have this relation. And okay, because we know VW prime is just the partial phi, partial y. Okay, let's move further. And so we have this relation, and then we can also write down YW. So by combining these two, we have partial phi, partial y at the wall, and it can be expressed by this sine function. Because y is small and close to 0, and that's because we consider the wavelength is amplitude is small. Okay, so and then we can get the partial phi partial y at the wall can be expressed by the function on the right hand side. So now we can look at the equation about gy. So, and now we are applying boundary condition 1. When y goes to infinity, the height goes to the free stream, and v should be remain a finite value. So I'm rewriting the gy in here. So now let's look at the second part on the right hand side. If y goes to infinity, we assume k is a positive number. And then the second term on the right hand side goes to infinity, and so this violates with boundary condition 1. So that means a2 should be 0. So then we don't have the problem of going to infinity. Okay, so then phi xy can be rewritten. Yeah. So now we do the partial phi partial y on for phi xy. Okay, so we have the expression. And then at wall, we are just letting y being 0, so it becomes this one. And it should be also to the right hand side, which we have derived in the previous slide. Also in here, we can derive it. Okay, so finally, by doing one-to-one comparison, we can know B2 equals 0, and A1, we can also find A1. And also k. So now we know a1, b2, and k, and also a2 is 0. Okay, so now we can have the perturbation velocity potential. It's in this equation. And similarly, we can have the perturbation velocity. So just to do the partial difference of partial phi, partial x, we have the perturbation velocity. And then we can have pressure coefficient, Cp. And this is, we derive Cp relation in the transonic flow, especially when we make use of the compressibility correction. So we have the Cp, and naturally we also have the pressure coefficient on the wall. Okay, so now we finished that question. So now we see an example with some numbers. Now the wavy wall has wavelength of 1 meter, the amplitude is 0.03 meter, the free stream Mach number is 0.6, and the free stream velocity is 214 meter per second, and the velocity potential can be expressed this way. Okay, so now the original form is like this. So this is called actually the perturbation velocity potential. The above one is the velocity potential. That's the difference. So the difference is 214 times x. So that's a difference. And so I have a MATLAB code to apply this equation. And then we can plot the velocity contour for u and v. And we can see, for example, on the u velocity contour, and on the top of the wavelength, that there is a high speed velocity, but at the groove of the wavelength, we have low speed velocity. Okay, and if we have a plot of the velocity vectors, we can see the velocity vectors are nicely tangential to the surface, follow the wavelength. You can see, yeah. And so because I wrote it into a program, we have the flexibility to change the parameters. Now what I'm changing is the amplitude. So the amplitude h is also changed to 0.09 meter and 0.15 meter. So you can see when h goes up to 0.09 meter, and we can see there's a stagnation about to happen, which means the flow is going to separate. And once h is going to be 0.15 meter, so that's 15 centimeters, and we already see the reverse flow. So I would say it's not correct. Just let you see the trend. Because why it's not correct? Because when we the derived velocity potential equation is just based on small disturbance assumption. But now, if we increase the wavelength amplitude to like 15 centimeter, it's already 15% of the chord. So it's no longer small amplitude. So that's why it is, you won't get the correct flow, because the flow separation will not happen like this. Is that right? But it tells us a trend. And so in above two cases, the wavelength amplitude is no longer small compared to the wavelength. Flow separation or stagnation can be observed, which violates against the small disturbance assumption. But although it's not incorrect, but we can still see the trend. And also it's quite interesting to see, is that right? And I would say this is a way people solve the fluid mechanics problems before the invention of computer. So we know the pressure coefficient can be expressed this way. Now we can have a look at the pressure distribution on the wall. So for the same problem, okay. So this is the black line is the wall boundary, and the blue curve is the pressure distribution. And you can see the wall wavelength and the pressure distribution are out of phase. And now I'm highlighting two portions of the profile. Why? Because that kind of hump shape is similar as either the top surface or lower surface of an airfoil, right? And we can see in that two highlighted regions, we have symmetrical distribution of the pressure coefficient. Both are being negative, which means the pressure over the surface is less than the free stream. Okay, so now the question is, will there be any drag on this surface, on the highlighted surface? And I give you a second to consider. Because we already know the CP, we should be able to find the force acting on the surface. Is that right? Okay, so we can overlap the force because the pressure is lower, so there are forces acting on the leading edge and the trailing edge of the surface, and they are symmetrical with respect to the center line. We can find the horizontal force which are relevant with the drag, and they are exactly counter each other, so the horizontal force will be cancelled. In that sense, there will be no drag force for the supersonic flow. This is a very important conclusion. No drag force, no net drag force acting on the portion of the wall, the highlighted portion. And we will compare this with the supersonic flow for exactly the same wall wavelength.